Live. Okay, hi everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see a bunch of questions here. Let's see, how about one from Morten here? Why does an electron fall or go to a lower orbit after being in an excited state? Okay, that requires explaining various things. Okay, so first point, atoms. In the center of an atom is its nucleus, made of protons and neutrons, and then outside there are electrons. People often say the electrons are orbiting the center of the atom. That's kind of a rather idealized way to think about what's going on, but more or less you could start off by thinking that. And the nucleus is pretty small compared to where the electrons orbit. The nucleus is about 100,000 times smaller than the radius of the orbit, so to speak. Why does an electron, quotes, orbit the nucleus? Well, the nucleus is made of protons, which are positively charged, and neutrons, which are neutral, electrically neutral, and electrons are negatively charged. And there's just a rule about electricity that unlike charges attract. So positive charge in the nucleus attracts the negative charge, which is the electron, and it kind of keeps the electron from sort of just floating away out into the distance, and it keeps it sort of in somewhere near the nucleus. Now, why does the electron not just, given that there's this force of attraction between the nucleus and the electron, why does the electron not just get pulled right into the nucleus and then go splat there? Why doesn't it just sort of crash into the nucleus? Well, that fact that the electron doesn't do that is what led people to, one of the main things that led people to invent quantum mechanics and quantum theory about 100 years ago. It's an observation that electrons can't just, in order for the electron to just sort of spiral in towards the nucleus, it has to change the amount of energy that it has. It has to sort of continuously change the amount of energy that it has. As it goes in towards the nucleus, it will gradually have less and less force of attraction, less and less potential energy, maybe more kinetic energy of motion as it spirals faster and so on. It has to change the amount of energy that it has in some continuous way. And sort of one of the key observations of quantum mechanics is that electrons don't do that. Instead, when they are confined within an atom, at least, they have a discrete set of possible energy levels. They're only, an electron can have a particular energy or some other energy or some other energy, but it can't have energies in between those energy levels. So in a hydrogen atom, for example, there's the question of, okay, so what energy can an electron have? Well, the way that this is thought about sort of in the mathematics of quantum theory, usually a thing called Schrodinger's equation. And Schrodinger's equation is an equation that determines, it's determining more or less the probability for where an electron should be. And the equation, you can think of the relevant part of the equation as being a little bit like the equation that governs waves on a string. So for example, if you have a piece of string, you hold it at the two ends and you pluck it in the middle, you can have a mode of the string where the string has just got one, it's just been plucked in the middle and it's bouncing back and forth like that. Or you can have a mode of the string where it's got where it has two peaks, where it has it's pulled out here and it goes out again on the other side, and that's another mode of the string. And in general, with something like an at least idealized string, you'll find that there are modes of the string which have both the lowest frequency where it just has a single kind of hump, then the next frequency where it has two humps, then one where it has three humps, and so on. And the frequency can go up, it can be any whole number, any integer number of humps that it can have, but it can't have 3.5 humps. Because if it had 3.5 humps, the last hump wouldn't be sort of over. And if you attach the string at a particular level, then you would be sort of in the middle of a hump where you want to attach the string, and that wouldn't work. So as soon as you have, say, I'm attaching the string at this fixed level here, and then I'm going to let it bow out in one direction or the other, you have to have a fixed set of possible modes of the string. So that exact same thing happens in the mathematics of Schrödinger's equation for an electron in a hydrogen atom or in an atom, that there are a certain number of possible modes that the electron can exist in. And the lowest mode is something where more or less it just has a single, this so-called wave function for the electron just has a single peak. And if you have, if you go to the next mode, it kind of has two peaks and so on. It's pretty much like waves on it, like these modes of a string, although the detailed mathematics is a bit different. If you're into these things, for modes on a string, they're trigonometric functions, sine functions, cosine functions, and so on. For the wave function for like a single electron in a hydrogen atom, which has just one proton, the relevant functions are things called spherical harmonics, which are the 3D generalization of sine functions, together with things called Laguerre polynomials, which are the things that determine the kind of radial behavior of as a function of distance from the nucleus. But the main point is, because of the electrical attraction of the electron to the nucleus, it's held sort of in this fixed region, more or less, just as kind of you're imagining a string held in a fixed way. And it's that, together with the fact that this just fact about quantum mechanics, that leads the electron to just have this discrete set of possible energy levels. And those discrete energy levels, you can have an electron in its ground state, its lowest energy level, or its first excited state, or its second excited state, and so on and so on and so on. In the case of a hydrogen atom, simplest kind of atom with just one proton, one electron, the energy levels are roughly spaced like 1 over n squared. The nth level is roughly, as you go towards the point at which the electron, which you pump so much energy into the electron just says, I'm out of here, and escapes from the atomic nucleus. As you approach that point, you have lots and lots of energy levels all kind of accumulating together, but there's just that simple formula that tells you the energy levels for an electron in a hydrogen atom. So the question was, what happens when an electron is in an excited state and then decays into the ground state? So there are all kinds of ways the electron can wind up in an excited state. For example, you could have the atom at a high temperature. What does that mean? The temperature, it tells you that how fast the atom is just running around, the energy associated with just the motion of the atom. And when an atom is kind of running around in a gas or something, it will collide with other atoms. And those collisions will as those collisions happen, they're essentially electrical forces that get imposed on the electron in the atom, and the electron will be pushed to a higher energy level. And the kind of rules of quantum mechanics say that the electron has to be pushed from one energy level to the next energy level to the next energy level. It can't be anywhere in between those. It has to make these jumps between energy levels. And now actually, to be a little bit more accurate about what quantum mechanics really says, there's this thing called the uncertainty principle in quantum mechanics, which essentially tells you this thing where you have, it's got to be at a particular energy level, that applies if you're going to say that's what the atom is like and it's staying that way. But if you say what can happen just for a very brief time, you can actually have something which is not quite what you would expect from, oh, it's got this energy level. There's an uncertainty in the energy, and what happens is the uncertainty in the energy is inversely proportional to the uncertainty in the time, so to speak. So that means if you wait a really long time, the energy is very, very precisely defined. If you wait only a very short time, if you look at things only in a very short time interval, the energy can fluctuate. And so, but in any case, when you have an atom that's kind of running around in a gas, the electrons can get energy given to them. They can end up in excited states. Now the question is, what will happen to an electron that is in that excited state? And the answer is that the electron will have some probability to emit a photon and jump down to the lower state. So why does it do that? Well, there are a variety of ways to think about this. One way to think about it is, let's see, what's the best way to think about it? Well, we could think about it again. It's kind of a rule about quantum mechanics that says there is a certain probability for an electron to emit a photon, and that's something where the again, this is a little complicated. Okay, if you have an electron and it's just going along and it's just sort of freely moving through the vacuum, then it's not possible for the electron to emit a photon because momentum conservation prevents that. If you can't arrange to conserve momentum and do that. So what ends up happening? Well, actually, that's not. Yeah, okay. Here's the problem. If you've got an electron, then it can't emit a photon and stay being an electron. You could have one thing that's pretty common in particle physics is you have unstable particles. You have one type of particle, like, I don't know, a pion, for example. And after some amount of time, this pion has some mass, and after some amount of time, there's a distribution. It's an exponential distribution of how long it takes. But after it has some lifetime, and on average, after a certain amount of time, the pion will just break up into two particles. But neither of those final particles can be a pion because energy and momentum conservation can't still work if one of those final particles is the same as one of the initial particles. So for an electron that's just tooling along, that's just happily going through the vacuum, it can't just emit an actual photon. If you kick the electron with some other force, then absolutely the electron can emit a photon. And so what happens in one way to think about it is that at any given moment, an electron has some chance of emitting a photon, but it can't actually do it unless it's sort of been kind of kicked and given some momentum, for example. Well, when an electron is held inside an atom, it's constantly being kind of kicked by the forces that keep the electron kind of in orbit in a sense in the atom. More exactly, there's this idea of virtual photons. A real photon is a photon that it's emitted and it can go off and it can survive for millions of years and it can just go through space forever. A virtual photon, just like I mentioned, there's this uncertainty principle that talks about how you can have a variation of energy for a sufficiently short time, and for a short enough time, there can be a variation of energy. So similarly, that same kind of uncertainty principle idea has the feature that for a short enough time, even the number of particles that you thought you had isn't something that is fixed. So there's sort of an uncertainty idea. It's a general idea of quantum mechanics and its fancier version, quantum field theory, that says if you are only dealing with a short enough time interval, there's sort of even uncertainty in the number of particles you thought you had. And so what that allows to happen is that an electron can emit virtual photons, which it then reabsorbs again a very short time afterwards. So for some brief period of time, you might have thought you had one particle, but actually you have two. It's an electron and a virtual photon. Okay, so electrical forces of like the atomic nucleus keeping the electron in its orbit, those can be thought about as lots of exchange of virtual photons between the nucleus and the electron. And so those virtual photons are sort of continually kicking the electron that is in its orbit, so to speak, around the nucleus. And those kicks allow the possibility of the electron emitting an actual photon, an actual particle of light. And so what happens is there's some chance that it does that. If it's going to do that, it has to emit a photon whose energy is exactly the difference of energies between the excited, if it's in the first excited state, between that excited state and the ground state. And so, because that's the only amount of energy that you could allow to be emitted, because the electron has to wind up jumping down to the lower energy state. But so with some chance, when the thing is in that excited state, it will emit a photon, and because it's continually being kicked, so it sort of has the chance to emit a photon, and with some probability, after some amount of time, on average, it will emit a photon and jump down to the lower state. When it emits that photon, it produces, that might produce visible light if it's at the right energy difference. And that's, for example, the visible light that you see in a fluorescent light bulb. That's the what's happening is that there have been atoms that have been sort of with electrons that have been excited, in that case by electric discharge, and the electrons are kind of jumping down to the lower state, emitting a photon of a particular energy. And so if you looked at the frequencies of the light that were emitted, there'll be these specific spectral lines, as they're called, specific frequencies of light that are being emitted associated with a specific jumping down from an excited state to the ground state for the atom. So that's sorry, this has actually got a little bit more complicated than I thought. It requires explaining a little bit of quantum mechanics and things to see how that works. But that's kind of the idea of why the electron sort of jumps down to the lower state. Is there's always this possibility of emitting a photon, and as soon as that happens, it can jump down to the lower state, or has to jump down to the lower state. Just in sort of, there are more complicated things that can happen with very low probability, like you can emit 2 photons and they can have slightly different energies and things like that. But most of the time, it's you're in an excited state, you emit a single photon, you jump down to the lower state. Let's see. Oh boy, there's a question from Vuk here. What does the fact that there are an infinite number of decimals between 2 integers tell us about the nature of the world? Okay, well, let's first of all talk about what that means. So we have numbers, 0, 1, 2, 3, etc. In between 0 and 1, there are an infinite number of numbers that you can name. There's, 0.1, there's 0.01, there's 0.11111, 2, 3, 4, 5, 6. These are all decimal numbers, and there's an infinite number of decimal numbers that fit in between any 2 integers like 0 and 1. And so the this question of whether the there's this kind of there are an infinite number of integers, 0, 1, 2, 3, 4, 5, you can keep counting forever, but between any 2 integers, there are an infinite number of so-called real numbers that you can specify with decimals. And each of those decimals, the reason that, in a sense, that they're an infinite number of real numbers is that each one of those decimals can keep going forever. So you can just make a change to a digit that's the billionth digit, and that will give you a new real number. And it's incredibly close to the real number you had before, but you can pack an infinite number of real numbers in between, let's say, 0 and 1. Now, things get kind of tricky because you can ask questions like, well, what about rational numbers? What about numbers of the form 2/3 or 3/4 or whatever else? And you can say, as you go and look at sort of all possible numbers that you can make from rational numbers, that also you can pack an infinite number of those things in between 0 and 1. And so those are 2 different kinds of ways to get an infinite number of numbers between 0 and 1. One is you just pick the digits in the decimal expansion, and another is you form them by taking 2 integers and you say this integer divided by that integer. Those are sort of 2 ways to pack infinite numbers of numbers in between 0 and 1. And there are subtle mathematical things we could separately talk about that have to do with sort of the difference in thinking about those 2 different kinds of ways to pack infinite numbers of numbers into this interval of the real line, so to speak. Okay, what does this tell us about the nature of the world was the question. I think it tells us less than we might think it tells us, because I don't think that our physical universe is capable of representing those precise real numbers that exist, those infinite number of precise real numbers that, let's say, exist between 0 and 1. So it used to be thought that, for example, if you look at space, if you just say, I have a point, I can pick its position, I can give it coordinates. Those coordinates can be arbitrary numbers with as many decimal digits as I want. It used to be thought that it was perfectly okay in the universe to just say, I've got one point here that has these coordinates, I've got another point here that is infinitesimally away, that has this coordinate that differs only in the billionth digit, and I can pack as many points as I want into an arbitrarily small region of space. That's what people used to think. Actually, a long time ago, people used to think similar things about fluids like water, that you could like be at any position in some water because it's just a continuous fluid. But then about 150 years ago, it became clear that no, that's not true about water. You can't just be at any position in water because water is actually made of discrete molecules, and you either are at the position of a molecule or between molecules. And you can't just sort of pick an absolutely arbitrary position to be at in something like a fluid like water. So the question is, how does this work for space? One of the things that's come out of our big effort to find a fundamental theory of physics in the last couple of years has been really pretty good evidence that space, like water, consists of discrete things, and that it isn't the case that you can put, that in fact space, there are sort of atoms of space. They're much more kind of idealized things than physical atoms like of hydrogen or something. They're just sort of these elements that make up the universe. They're kind of the ultimate elements that make up the universe, but you can think of them as playing the role of kind of atoms of space. And space consists of this huge number of these sort of discrete points. So it isn't the case that you can just sort of, if you say, well, where can I go in space? Well, you can go at any of these points, the positions of any of these atoms of space, but you can't in some sense go anywhere between them. Now, we can't tell that space is made of discrete atoms of space because we don't really know the scale yet, but perhaps the scale of the distance between sort of neighboring atoms of space might be something like 1 trillion trillionth of a meter. So really, really small, incredibly much smaller than, for example, the size of a proton. We don't know how big electrons are. So far as we can tell, electrons in experiments so far, they look like they're infinitely small. I don't think that's really the case. I think that actually electrons are quite big compared to this kind of elementary length, this sort of shortest distance between atoms of space. But as soon as you imagine that the universe consists of discrete points, discrete atoms of space, it no longer becomes possible to say, oh, we'll just pick an arbitrary position. Now, so this idea that we can use real numbers to represent things in the universe, ultimately, I don't think that can be true. Ultimately, I think that there are just discrete positions that you can have, for example. Now, it is the case, though, that the mathematics that you can get by assuming that things are continuous, assuming that you can just vary things arbitrarily small amount, that you vary something an arbitrarily small amount, something else will vary an arbitrarily small amount, and so on, that you can talk about arbitrarily tiny variations and the effect of arbitrary tiny variations. That's a very useful thing in mathematics. And that's one of the core things that leads one to calculus, for example. And it's a very useful assumption in mathematics. And a lot of mathematical structure can be built on top of this kind of assumption of continuity. So at least as an approximation to what happens in the real world, it's an important thing to use because it allows you to build this kind of tower of mathematics. I don't think it's how it actually works in the real world. I think that there will be situations, we imagine there might be some in kind of extremal versions of black holes and other rather exotic things, where you can actually see through to the atoms of space. You can actually see that space is discrete. You can tell it's kind of like a kind of a gravitational analog of a microscope, where you're kind of seeing down to the smallest scales of space. And you can tell that it's no longer continuous, just like there are experiments you can do on water that show that, yes, it's actually made of discrete molecules, not something continuous. So I think the answer is that I view kind of the idea of real numbers and the idea of the sort of continuous variation, you can go arbitrarily closely to get from one number to the next. I view that as being a useful idealization that lets you build a bunch of mathematics, but not really the way the world actually works. So there's a question here. Okay. It's a question from M. Rector. What is a time crystal? I believe that term was invented by a chap I know named Frank Wilczek, who's a physicist. But so I'm going to say what my interpretation of it is, and I hope I'm right in this. So first of all, what is a crystal? The defining feature of a crystal is that there are atoms arranged in a particular way, and as you move around the crystal, you'll always find atoms arranged in the same way. So for example, a salt crystal, a sodium chloride crystal, the atoms are arranged essentially in a cubic grid. So they're just arranged like I don't know, I was going to say like an egg crate, but I think egg crates, I haven't seen an egg crate in decades. So I'm not sure that's a useful analogy, but they're basically just arranged, understand a square grid, a cubic grid. That's how the atoms are arranged in a sodium chloride crystal. And the defining feature of it being a crystal is that it is, if you move to a different part of the crystal, you'll still see it's arranged in a cubic way. And if you know that if you're in this particular position in the crystal and you move by a certain number of so-called lattice spacings, or a certain number of multiples of the size of the unit cell, the thing that just contains the defining unit, which is a cube in the case of a cubic thing in the case of sodium chloride. If you move around by the sort of size of that unit cell, you'll just keep getting copies of that unit cell. The crystal will always keep looking the same. So that's how an ordinary crystal works. There are, let's see, 17, I think, different kinds of arrangements of possible sort of arrangements of lattices for three-dimensional crystals. There's like the way the diamond crystals work. There's ways that hexagonal close packed crystals, which are like packed, where the atoms are packed in the way that people pack spherical fruit in a grocery store and so on. There are different kinds of packings for the different kinds of ways to arrange those unit cells. And the mathematics of group theory tells one that there are a limited number, so I remember correctly, there are 17 of these so-called Bravais lattices that define the possible arrangements that you can have. And so that's how crystals work. That's how ordinary crystals work. They are crystals in space. So there are other kinds of crystals. Another kind of crystal is a liquid crystal. What is a liquid crystal? Well, a liquid crystal, there are a bunch of liquid crystal are molecules, often cholesterol-like molecules, which are long, stringy molecules, and they have a definite kind of direction to them. And what happens in a liquid crystal is the molecules are sort of bouncing around in all different places, but what makes them sort of crystalline is that they are lined up. There are all these kinds of directions. So in direction, there is this kind of order that exists, just like in the case of an ordinary crystal. In position, there's a certain kind of order that exists. So the idea of a time crystal is to say, let's imagine something which is changing through time. You can have something where there is the thing kind of repeats itself in time, just like in an ordinary crystal, the thing repeats itself in space. And I'm not sure there are many phenomena where the thing will tend to be, but something will happen periodically in time. You have a pendulum, it's swinging backwards and forwards. It's periodic in time. The idea of a time crystal, I think, is that you have something where there are many, many different components, just like there are many different atoms in a crystal and an ordinary crystal, and they're all arranged a certain way in space. I think in a time crystal, the idea is that there are many components that are all having this sort of order in time. I'm not sure. I think that's the idea there. Let's see. It's a question from, okay, let's change topic completely. There's a question from Wraith. What is my opinion on the technological and economic feasibility of asteroid mining? You know, the world is a very strange place when, okay, so first of all, yeah, I was going to say about asteroid mining, somehow it's a staple of kind of science fiction. Let's go to asteroids and go mine something interesting from asteroids. You know, I'm kind of waiting for the day when somebody identifies a golden asteroid, where there's an asteroid that's all made of gold. One of the things that's weird about minerals, mining, those kinds of things, is that there are places where there's a deposit where there's lots of some kind of mineral, and there are other places where there's none of it. Like on the Earth, there are places where we say, oh yeah, that's a great place for copper mining, or oh, there's a you know, molybdenum, you can get molybdenum here, or oh, this is a place where you can get europium or some other obscure element. So, and there are, you know, around the world, there are places where there's specific places where there are gold mines, uranium mines. You know, there, even if you go to Colorado, there are cities named after the different kinds of elements and minerals that got mined there back in the day, and so on. So for some reason on the Earth, for example, there will be particular places where there's a big deposit of gold or a big deposit of molybdenum. And that happens presumably when the Earth was formed, and as sort of all these different chemical elements were part of kind of this molten thing that was forming the Earth, and various processes of, oh, there's this temperature gradient that causes this thing to go to this place and this one to go to that place. And that sort of separated these different things and wind them up being in different places. I must say that I find it a little bit confusing, because I don't think, I might be wrong about this, but I don't think in the sun, for example, I don't think there are similarly places where if you look at the sun, and maybe that's just the outer layers of the sun, that this is the case. I don't think it's true that you can say, oh, there's a very helium-rich part of the sun, there's a very hydrogen-rich part of the sun. I think it's pretty uniform. But for whatever reason, the crust of the Earth is not that way. And so we have definite deposits of this there. And, you know, some country can really luck out, Rwanda can really luck out in having a lot of tantalum ore in its rocks or whatever else it is. And so there's segregation of where things go. And similarly in the asteroid belt, of these little fragments of rock, basically, that mostly orbit between the orbits of Mars and Jupiter, and that were presumably things that were never accreted into planets when the solar system formed, or conceivably some of them are the result of collisions between planets that sort of self-destructed and turned into a bunch of pieces of rubble, so to speak. But within the asteroid belt, there are similarly, there seem to be asteroids that are made, very rich in one material, very rich in another material. And so you can imagine going and finding the golden asteroid, so to speak. Now, the question is, what do you do with the golden asteroid? You have to go and send a spacecraft there and sort of bring, there are various different schemes. If it's a small enough asteroid, you can imagine just attaching rocket engines to the asteroid and turning it into a rocket and just bringing it back to Earth. It's a little bit like back in the day, people used to take icebergs from the Arctic, for example, and they used to tow them through the Atlantic, for example, down to like New York City and places like that before air conditioning and so on, and refrigeration was really so much of a thing. And the rate at which the ice melts is slow enough that you can get the iceberg, all the way to New York and then start chopping pieces off it to deliver ice to people. And so it's sort of that's one approach that's reminiscent of that, is just put a bunch of rockets on a little asteroid and have it come over and wind up in Earth orbit or something like this, or maybe even make it re-enter the Earth's atmosphere. I'm not sure if that's possible. I don't know how much you lose of the asteroid if you have it operate like a meteorite, so to speak. There are all kinds of questions about if you go out and stake a claim to an asteroid, like who owns the asteroids? And there are various treaties that some countries have subscribed to about sort of ownership of things in outer space. And I kind of think it's probably at this point, if somebody actually went and staked a claim to an asteroid, it's probably for all practical purposes their asteroid. But it's not completely clear how that works. But so that's sort of an issue. In the case of mineral rights, there's a very well-defined protocol for how you sort of stake a claim and then are able to make use of those minerals in a particular place on the Earth. The question of different schemes for mining asteroids, I've certainly seen a few of these sort of plans for how you would do it. I have no idea if it makes any economic sense. I think that it's one of these things where, you know, mining it for gold, it's kind of a weird idea because, you know, if it is the case that you tow the giant golden asteroid into Earth orbit, the price of gold, where people have hoarded gold, you know, to maintain, to sort of represent the value of some currency or some such other thing, the hoarding of gold, it's all going to get completely broken if somebody shows up in Earth orbit with a giant golden asteroid. I mean, the same kind of thing happened back, what was it, 30 years ago or something, with the price of silver. The price of silver was going up and up and up. And eventually it became clear that at some point, people will take, well, random silver spoons they have, but also could actually mine more silver out of the ground. And although it's expensive to do that mining, at some point, it means, oh, there's tons more silver. And so the price of silver went way down. And I kind of think that's what would happen if somebody shows up with a golden asteroid in Earth orbit. Now, you know, there are other kinds of materials where you say, you know, we really need more, pick your material. You know, let's say that the cold fusion scheme that used palladium had really worked. And people were like, we really need more palladium. Or let's say the high temperature superconductor scheme that used lanthanum had really worked. You know, we need tons of lanthanum, but it's a so-called rare earth element on the Earth, and there's not very much of it. I can tell you a funny story from a slightly obscure element, gallium. It has become more commonly used in the intervening years, but back in the early-ish 1980s, I was interacting with some physicists who really needed 10 tons of gallium. Okay, and why do they need 10 tons of gallium? They were going to use it as a detector for neutrinos. And they were just going to take the 10 tons of gallium, stick it in a mine somewhere for 10 years, you know, have all kinds of detectors that allowed you to detect particles going through it, and they were going to give it back to somebody. And at that time, I kind of investigated the question, how much gallium actually is there in the world and who has it? And it turns out there were about 10 tons of gallium that had been mined and were stockpiled at that time. So that gives you some kind of sense of how much of one of these kind of rare materials exists. And clearly, if you find an asteroid made of gallium, it'll be a lot, well, the typical, you know, you can find asteroids much bigger than 10 tons. So if there's one very rich in gallium, it could be a good thing. Now, in fact, I think much more gallium has been found since then. I think people just didn't care about mining it. It was mined along with aluminum back in those days. But I think nobody really needed it for anything, so nobody bothered to mine it. And as it became needed for various electronic components, people started actually mining it and refining it and so on. So but I was going to say at the beginning of this, the question of asteroid mining, it was a couple of years ago, I had was a company that was an asteroid mining company. Now, obviously, it's not in production, in operation, because there are no asteroids being mined right now, but it was a company that was kind of making the plans for mining asteroids. And it ended up being bought by a blockchain company. And it's like, this is a very strange thing in the world. And I happened to run into the CEO of the asteroid mining company. And I was like, why did this blockchain company buy you? It wasn't the coincidence of the word mining in asteroid mining and mining as in the idea of mining for proof of work in blockchains and things. And it's like, well, it wasn't quite that, but not clear how close it wasn't to that, so to speak. Of course, the other thing that is interesting about things like asteroids and asteroid mining and so on is this kind of almost legalistic question about staking claims to asteroids and kind of how you remake kind of property laws when you're dealing with extraterrestrial objects and so on. Let's see. Oh boy, there's a question here. Okay, there's a question from Ori. How does sophisticated philosophy relate to sophisticated math in the thinking processes underlying them and the intellectual firepower in effect? It's an interesting question. So, you know, mathematics is a very, it's a thing where you can build a very tall tower. You have some ideas in mathematics, and on top of those elementary ideas, like adding numbers together, then you get powers of numbers, then you get numbers of different kinds, then you get sort of ways to factor numbers, you get ways to combine numbers. You build this big, big, big tower of different kinds of knowledge. And so mathematics, as it exists today, a lot of the top of the tower involves kind of many steps from kind of elementary notions, like notions of whole numbers and notions of, I don't know, angles or something like this. The thing that's built is a very tall tower. And that's kind of the nature of mathematical work, is that there's this kind of tall tower of concepts that build on top of each other. Let's contrast that with philosophy. In philosophy, it tends to be the case that there are difficult concepts, but there is much less of this phenomenon of things building in a tower. It's much more that, you know, questions that were asked by Plato back a couple of thousand years ago are still reasonable questions you can ask today, and you can reason about those questions, and the arguments have changed and gotten a bit more sophisticated, and there are a few more steps, but there's nothing like the kind of giant tower that gets built in mathematics. One's still dealing with sort of philosophy. The methodology is much more about, can we take this rock that's been around for a long time and can we polish it in a new way, rather than can we build a big tower of rocks and look only at the rock at the top, so to speak. It's a somewhat different kind of practice of activity. And that's why, for example, when you look at a philosophy paper, it might routinely refer to papers that are 500 years, thousands of years old, whereas in mathematics, that will be much rarer. In mathematics, the things that were figured out by Gauss and Euler and so on, most research mathematics has long ago kind of covered those things in more layers of abstraction and built more sort of sophisticated concepts on top of that. Now, in terms of the type of thinking that's involved in these different areas, I can't say I'm a full native in either of these areas, but I would say that my observation is that sort of the mode of work in philosophy is the medium of explanation is basically natural language. You explain philosophy by writing essays about it, mostly. There's a few areas of philosophy which have some notational kinds of things, but mostly you write essays about things. Whereas in mathematics, most of the explanation is done at the level of sort of formal mathematical presentation in the sort of mathematical language that exists for mathematics. There is no similar language for philosophy. Back in the 1600s, people talked about making a philosophical language, which would be some kind of formal notation for the kinds of ideas that might occur both in sort of everyday discourse and in the kinds of things one talks about in philosophy, whether it's about ethics or epistemology or any of these different areas. That effort to make a philosophical language didn't really get off the ground in the 1600s. I think actually there's the chance to do it again now. And in fact, the things I built with kind of computational language as a way in Wolfram language, for example, to represent the world computationally, that's kind of going in the direction of making something like this kind of philosophical language. If we have a kind of formal philosophical language, then we may be able to start building towers in philosophy, much as we have built towers in mathematics ever since mathematical notation was invented, which is basically 400 years ago. And that's what began the towers of things like algebra and calculus and so on beyond that. In terms of actual people who do mathematics versus do philosophy, I must say I've noticed some things which are kind of interesting, like in many areas of science, if you're talking to a scientist, they'll kind of be just listening for the point. They just want to know, you got one punchy point to make. It's like, this is the result, theorem in mathematics, some observational fact in physics, whatever else. It's like, listen for the point. And they don't really read all the details and so on and so on and so on. Philosophers, on the other hand, tend to be not that way. They tend to actually read the details because that's where their content really is. It's not, there's just one punchy point. It's not, oh, we can summarize Wittgenstein by one sentence. It's the message is in that whole sort of essay structure that builds up those ideas. So it's a little different. In mathematics, people will say, well, tell me the theorem. Okay, great. Now show me the proof of the theorem. Okay, that helps me to understand the context of the theorem, maybe. If it's an automated proof, it probably doesn't help you with very much. But if it's a handmade proof, it's part of the exposition of the theorem itself. So that's sort of a difference in the way that works. In terms of, you can ask questions. I always think it's kind of a silly question to, it's a dumb question to ask how smart the people are who do different kinds of things, because I don't think there's really a meaning to that. I think that if you look at the kind of turns of mind required in philosophy and in mathematics, I have the impression, I might be wrong, that there is more diversity in the types of ways to do mathematics than there are in the types of ways to do philosophy. I think in philosophy, it's really about keeping the argument in mind, so to speak, and being able to figure out how all the different things that sort of emerge in that argument and how you clarify the argument so that you can go and take the next step and so on. In mathematics, there tend to be people who have a very formal approach where it's like, we've got this formal structure, we can calculate from it. There are people who have a rather more intuitive aesthetic approach. We say, we just imagine these concepts and we can just sort of see them flowing around and this must fit with that in this or that way. There are people who have a very geometrical view of things of, I can just imagine these different objects, even if they're in, infinite dimensional space or whatever else. I kind of have a geometrical way of thinking about that. There are people who have a much more algebraic way of thinking about things, where it's really like, give me the formal structure written down in symbols and see what consequences it has. So that's a little bit on kind of the sort of a little bit of at least how I see the relationship between kind of the things people do in philosophy and in mathematics. That both of them, when done well, involve a clarity of thought and presentation that is somewhat similar. I would say that philosophy tends to be the catch-all field of, if you can't figure out anything beyond what you can figure out by just words, then it's philosophy. If there's a formalism, if there's some kind of structured way of approaching it, as there is in mathematics, then it's not philosophy. And I think that in what tends to happen is that fields, when philosophy has been in sort of a top field, and has been at various times in history, that has been quite common for fields to be kind of born in philosophy. And then they develop a serious notation and a serious kind of formalism, and then they sort of drop out of philosophy and become their own field. I mean, back in the day, physics used to be called natural philosophy, and was thought of often as a branch of philosophy that had to do with reasoning about the natural world. But after Galileo and Newton and people like that, particularly after they introduced kind of mathematical thinking into physics and natural philosophy, physics kind of dropped out of the philosophy realm and became its own thing. I mean, famously, the title of Isaac Newton's 1687 book Principia Mathematica was translated into English, it will be Mathematical Principles of Natural Philosophy. So right there in the title, he was saying, natural philosophy, which is a branch of philosophy, these are the mathematical principles of it, which eventually became another kind of field. So I think that's, for myself, I've been quite interested in recent times in questions that have been questions of philosophy. But what I've found is that there are things that I've discovered in science that sort of really address those questions in philosophy. Questions about kind of what can we predict, what can we know, questions about, well, for example, why does the universe exist? These kinds of questions, which have been questions of philosophy. A question like, why does the universe exist? That's even philosophy says that question is not for us. And it's often kind of been pushed to theology, for example. Theology was the kind of the big tradition back more than 500 years ago now, where there was a big sort of intellectual tradition that was very deeply interwoven with philosophy at that time, and was kind of the starting point for a lot of kinds of thinking about a lot of kinds of things. I think much of that has sort of been taken over by more formalistic science in modern times. I think that, I've just been actually thinking about and writing about kind of the development of different paradigms in the history of science. And I think we can kind of identify 3 historical periods and paradigms. And I think we have the makings of a 4th one that are kind of interesting, but that's a different topic, which would get me far afield, and I'm happy to talk about it another time. Let's see, questions here. Let's see, there's a question from Erin. How did my parents encourage my pursuits in science? I think they mostly encouraged them by knowing almost nothing about science. That's a kind of a terrible thing to say, but I think it of course always depends on the personality of the child. But I think I was very happy knowing about things that my parents did not know about, and that happened to be science. I could have known about lots of other kinds of things my parents didn't know about, but I kind of learned about science as pretty much a personal, independent activity, not really particularly stimulated by parents or schools or anything like that. I just got interested in things and started wondering about different questions in science at the time when I was growing up in the 1960s. The space program was a big thing, and so that was kind of a particular kind of sort of thing that one was constantly hearing about, and it sounded kind of cool. And for me, it represented something which I suppose many young people think about, which is the space program was kind of an icon of the future, so to speak. And for me, since I was sort of planning to live in the future kind of thing, that was something that was pretty interesting to me. And from that, I got interested in more basic kinds of science and just reading books about science, learning stuff about science, trying to figure out things about science. That was kind of what happened. Now, amusingly, in terms of what I was just saying, my mother was actually a philosophy professor. And I suppose that the one thing that I might have gotten from that is if I would ever say anything about science, she would often say, but how could one possibly know that about some sort of scientific result? And so it was kind of an interesting exercise. She really knew basically nothing about the content of science, but it was like there was a certain degree of the way that knowledge is put together, so to speak, that I think one perhaps learns in learning about philosophy, that certainly had the interesting effect that if I really tried to explain something in that was kind of, you had to be able to explain it at a level where the sort of the structure of knowledge made sense, rather than just, well, here's this random fact. I'm not sure how much I really tried explaining that much there, but at least a little bit of that happened. I think my mother, particularly when I was quite young, I would be talking about things in science, and she would end up realizing that those were good examples that she could use in philosophy lectures she was giving and philosophy papers she wrote and so on. So no doubt I am pretty sure some of my early interest in, the typical kid things of dinosaurs and things like that wound up being sort of examples in philosophy papers and so on as a result of that. My father was mainly a business person and sometime novelist, and again, not very science oriented. I think had been interested in science a bit back in the 1940s and so on, but I think quickly decided that I knew more about science at a pretty young age than he knew, and he would just say silly things if he tried talking about it, which I don't think was quite true or fair. But so I would say that the number one feature of my sort of life in science there was that my parents didn't know much about it, and that was that for me was some. I actually, it would have been cool if they'd known a bunch about it. It would have been interesting. And had I, now that these days I'm interested in philosophy, I would have had much more interesting conversations with my mother about philosophy, given that I'm now interested in philosophy. But I wasn't back when I was much younger. So let's see, Vuk asks, if knowing absolutely nothing is represented by 0 and knowing everything is represented by 1, where do you think the human race is at the moment, and what are the limits of knowledge? One of the things that comes out of studying kind of computational kinds of ways of thinking about the world is the realization that the frontiers of knowledge are infinite. Essentially, it's like saying you can ask the question, given a particular way of constructing the world, what can you say everything about how the world will work? Can you invent everything that will be useful to us humans in dealing with the world? This question about can you say everything about how the world will work, the answer is you, for very fundamental reasons, cannot do that. It's related to Gödel's theorem in mathematics. It's related to this phenomenon I call computational irreducibility. That's a more general computational phenomenon. Basically, when you are running a program, which is kind of what we think is going on in the world, of things that happen in the world, and you say, what's this program going to do? Then we know for theoretical reasons that you could just see what the program does after some number of steps. But if we say, just tell me what it does in the end, after a trillion steps, a quadrillion steps, turns out we can never know the answer to that except by effectively following those trillion steps, quadrillion steps, whatever. Sometimes we can jump ahead, but often we cannot. Now, the fact that we often can't jump ahead, well, it turns out that that very fact implies that there are an infinite number of ways to jump ahead. Even though we can't in general jump ahead, there are an infinite number of specific cases in which we can jump ahead. In other words, what that means is if we're trying to figure out things about how the world works, there are an infinite number of things we can figure out, so-called computationally reducible facts that we can figure out, even though to figure out everything is impossible. And that manifests itself in mathematics as well. There's sort of an infinite frontier of possible theorems you can prove in mathematics. You'll never run out of theorems, at least in any theory that has the feature that it has computational irreducibility, and any sort of rich, interesting mathematical theory has that feature. You never run out of things to do. The big question is, when you prove that next theorem, when you make that next discovery about physics, when you invent that next invention, the question is, does anybody care? And that's more the question than, is there another thing out there to discover? Is there another thing out there to invent? There will always be more stuff to discover, more stuff to invent. The question is, when we figure out what we humans want, does it include those new things? So for example, in technology, we could say, I'm going to invent a thing that, I don't know, aligns human thoughts and makes them correspond to the thoughts of an ant. We say, right now, we'd say, that sounds pretty useless. We don't have a reason to have that right now. But in The question is, as we look at the progress of technology, I'll give you a better example of something, technology we have today, a treadmill, walking on a treadmill. Okay, so let's say you'd invented that in the Middle Ages. It's like people would look at that and say, why do we want this? What is this? What is the point of this? Oh, it's for taking exercise. What do you mean? I can take, I just walk around, whatever. It's like, well, it's for taking exercise if you're cooped up inside. And why do you want to take exercise? Well, makes you healthier and all those kinds of things. I think that the question of what, so a lot of what happens is asking the question, what is the, what is the thing that kind of humans care about to invent? There is an infinite frontier of things you could invent. The question is, which things are in the path that we humans think we care about? And let's see. So the question was, where are we humans in terms of going from no knowledge to all knowledge? We will never get to all knowledge. Now, there are various directions in which we may reach the edge of knowledge. For example, one that I've been much involved in is, do we know fundamentally how the universe works? I think we're finally fairly close to that. We know the underlying rules. We don't know what consequences those rules have. It's like we know the machine code for our computer, but there's an infinite number of possible programs that we're running on our computer and things we can do with our computer. But nevertheless, there's a question sort of in one direction of knowledge. There's a question of, do we know what the machine code for our universe is? And I think we're getting pretty close to that. I think we're at least going in the right direction. We have the right sort of formalism. We don't know all the details of how it works out, but we know much more closely how that's actually working. And that's kind of my personal and our excitement over the last couple of years, is figuring out how that works. So in that sense, one sort of border of knowledge, I think we are actually, surprisingly, did not think I would see this in my lifetime. I think we're surprisingly, we're hitting the edge of that. I think that there are when we look at building from that machine code, where can we build to? What kinds of things can we construct in the physical world? Well, that's an infinite frontier. Now, we can also ask the question, sort of an interesting question, when people learn about stuff, if there's an infinite frontier of knowledge, an infinite frontier of things to invent, how can it be the case that education remains finite? That is, it could be the case that over the course of history, as we learn more as a species and so on, we invent more. It could just be that we just need to learn more and more and more stuff. And that sort of, while we have right now, I don't know what it is, 8 years, 12 years, whatever of education, that, that could extend into, into some, you really need to be educated for 50 years just to know what's known about how the world works. Well, there is a certain sense in which that is happening because people learn about narrower and narrower pieces of what there is to know about everything, about how the world works and how to do things and so on. But actually, I think there's a different phenomenon as well, which is that as time goes forward, more things become abstracted away. So there was a time when to drive a car, you really had to know how a car works. You had to know, oh, you have to, pump this gas thing to get, to fill the fuel line, and you had to know how this works and that works and the other works. And, pretty soon it's just like press the button to make the car start, turn the key to make the car start, press the gas, car will go forward, turn the steering wheel. You don't need to know anything about how, all sorts of complicated things in the engine of the car are working. And so it is with lots of other kinds of areas that over time, more and more gets automated away, and we get to operate at a sort of higher level of abstraction. Both things get automated and we don't have to do them technologically, and things get understood better. And, there was a time when we would have had to learn all the different kinds of, animals maybe of some particular type, and then some classification of animals is put in place. We'd have to learn all the different kinds of mathematical curves of a certain type. And then there's a general theory of those things. And so we only have to learn the general theory. We don't need to learn all the detailed pieces. And so there's this trend towards higher abstraction and higher automation, and that reduces the amount that you need to know to be able to operate within those domains of knowledge in the world. And so that's sort of the counterbalancing force to there's just more and more and more to know, is more and more is getting sort of abstracted away. So in terms of what will sort of the growth of knowledge look like in the future, people are fond of saying, look, we have an exponentially increasing amount of sort of knowledge that's getting written down in papers about science and things like this. I'm not sure if that's a great reflection of what's really going on. I think it's just a question of how many people are doing science and what are the mechanisms for getting people to publish things and so on. I'm not sure that's really a reflection of the true sort of the true fundamental sort of knowledge that's being accumulated. And what tends to happen in the accumulation of knowledge is that particular areas suddenly open up. Whether it's, oh, now we have the idea of machine learning. Now we have the idea of blockchain. Now we have the idea of this fundamental theory of physics. These are things which are, in a sense, methodological areas that open up. And much of the progress of the dramatic progress of knowledge comes when when sort of a new methodological area opens up and people are able to explore that. And then there's typically a long period, 50, 100 years, whatever it is, when people are taking that methodological approach and saying, okay, we've got the idea of telescopes. Let's go use a telescope to look at all the things we can see. And most of those things are going to be, more of the same. And then occasionally there'll be some discovery made that way. But that's actually not such a good example. Better examples are things where one's doing some particular area of mathematical modeling or something like this, where it's like, we've got this basic idea, that all happened rather suddenly, and it immediately opened up all these different fields, and now we can start working with them. I mean, I will say that just to make a kind of a pre-thing for this kind of paradigm for thinking about theoretical science that I've been working on, that is something that's a consequence of what we've discovered in our physics project. It's kind of a different way of understanding kind of how to make fundamental models of things. And I'll talk about it, why not? I think one can kind of identify sort of, there are sort of, well, okay, I'll say this very briefly, and maybe I can talk about it some more in a different time. It's kind of, in antiquity, the big sort of realization about making models of things is that you could say, there's this definite thing, the universe is made of lots of copies of blah, blah, blah. Or, it's lots of polyhedra all stuffed together. It's lots of atoms. It's lots of this, lots of that. It's a kind of structural statement about what the universe is made of. That was kind of the first period of science, first big period of science, was just say, there's definite regularity in the universe. It's all made of copies of the same kind of thing. The second big period started in the 1600s when mathematics came in, and when one had the idea of basically writing down a mathematical equation or a mathematical formula to represent how the world works. And the next, I think, big sort of paradigmatic change, which I have to say I was personally much involved in the 1980s, is this 1980s to early 2000s, is kind of the idea of using programs and computations to represent what happens in the world. So instead of saying, I'm going to write down an equation and that's going to tell me everything about how some system is going to behave, you say, I'm going to write down a program, run the program, and you will see what the system will do. And so it's kind of like you're just given a program and the activity is run the program. It's not get the whole result, solve the equation and answer everything. It's rather run the program and specifically observe what it does. And so what happens in those different sort of paradigms, one of the things that happens is there's a different view of time in these different paradigms. In the kind of antiquity version, the sort of structural paradigm, you don't really talk about time. Things are just made of things, it's constructed in this way, etc. Time is not something that, there's some discussion of there there's a phenomenon that happens through time, but you don't think about dynamics of change and things like that in time, at least not as directly in the way the theory is set up. In the kind of mathematical period, time is just a variable, a coordinate. You solve the equation, time is a variable that appears, you set t equals 3.7, and you get the answer to what happens at time 3.7. So that's kind of the notion of time there. In the computational paradigm, time is something where the actual running of the program is the progress of time. And so there is something where the model itself contains sort of an irreducible effort needed to make progress in time, so to speak. Okay, so this fourth kind of paradigm is something that has kind of emerged as an important thing from our physics project, which is the idea that rather than in the computational paradigm where you just have a rule, you have the state of the world, you apply the rule, you get the new state of the world, and you keep doing that. It's kind of a sequential thing. There's this kind of multi-computational paradigm that we've realized is the relevant thing for understanding fundamental physics, in which you say, I have the state of the world, I'm going to apply a rule in many different ways. I'm going to get many states of the world. And then to those, I will apply rules in many ways. And I'll get this whole multi-way graph, we call it, of branching and merging kind of histories of states of the world, of possible states of the world. And when I say possible, that's a weird word, because in some sense, I think all those states of the world actually happen. And that's kind of the essence in the end of how quantum mechanics works. But the issue is, so in a sense then, whereas the computational paradigm has this thread of time that is associated with the progress of computation, the multi-computational paradigm has many threads of time. There are many threads of time branching and merging. There's no single sort of sequential notion of time. And what happens there is that one of the things is that we humans, to understand things, end up needing sequentialization of time. So we, in a sense, necessarily extract, we necessarily sort of make equivalent lots of different threads of time in this kind of multi-computational point of view. And those correspond to reference frames in relativity and various things in quantum measurement and so on, more technically. But essentially what's happening is that we are the observer, we are a necessary piece of this story, because without that, it's just like there are all these different threads of time, we can't tell what's going on. If we want to be able to tell anything about what's going on, to relate it to something human understandable, we have to sort of sequentialize time. We have to kind of make equivalences that allow us to have this single thread that we actually observe. And it turns out when you make that single thread you actually observe, there are some features of the way that the system is constructed, the way this kind of graph of multi-way graph of branching and merging pieces of history and so on, there are some inexorable features of that are basically a consequence of the construction of the whole thing. They don't depend on the details of the particular rules that you're using to figure out what the next state is from the previous state and so on. They are somehow somewhat generic features. And the fact that we're kind of making these observations is the sort of the simplicity of the observer forces a certain simplicity on the kinds of conclusions we can make, even though the underlying system is doing something very, very complicated. And that forcing of simplicity leads to a bunch of ideas, a bunch of approaches to actually making a kind of a science where you can explain things out of a lot of different fields, and I'm just exploring a bunch of these. I think I just added immunology to my list of immunology and neuroscience to my list of fields that I think they're going to be really interesting things to say with that kind of paradigm. But I think that this is an example of a place where, in a sense, this new paradigm will, I think, open up a bunch of new kinds of knowledge and new ways to talk about knowledge, new kinds of questions that you can ask about things that didn't exist before. And if you're just tracking, well, did we answer all the questions? Did we do all the exercises? The answer might be, we did all the exercises from the last version of what the kinds of questions were, but now we have this new paradigm that gives us a whole bunch of new questions we didn't even think of asking. And that's somewhat related to these questions about technology and what we humans want in technology, because that's, again, did we think we wanted a treadmill or something? And did we think we wanted to answer this kind of question? that's what gets opened up as we look at these different areas of knowledge and so on. And that's kind of, I think, that's why it's a little difficult to measure the progress of knowledge, because the knowledge, anytime you've got a measurement mechanism, you're locking yourself into that old kind of knowledge, not the new kind of knowledge for which your measurement doesn't really yet make sense. At least that's my impression here. Let's see, I need to wrap up soon here, but from Ruki, what could knowing the machine code of the universe unlock in technology? You know, it's an interesting question, because I sort of was saying, you know, it's going to be hundreds of years before anything useful comes from knowing directly for technology. And I was like giving analogies, like when Newton was figuring out his universal law of gravitation, you know, he knew that there could be artificial satellites orbiting the Earth, but he was kind of an investor in things. You know, he invested in the South Sea Company and all kinds of things like that. But had he invested in a rocket company back in the 1690s or something, it would have been a bad bet. Unfortunately, his investment in the South Sea Company was also a bad bet. But and that's its own bizarre, more biographical story about Newton. But in any case, so you know, from our physics project, it's like, is the only stuff that is in prospect like a rocket company seen from from the 1690s? I did figure out that there is some theoretical possibility of things like faster than light travel, that it becomes something which is a sort of a quotes engineering problem rather than a physics problem. Although to us today, it looks like an absolutely insurmountable engineering problem. But that's probably what satellite launches looked like in 1690. So the thing that's strange about our physics project is that it actually has, even a year later, it's starting to have applications. And it's like, how can that be? Well, the answer is its methodology is starting to have applications. Like its method of defining how you solve the Einstein equations for relativity, for general relativity and gravity, and describe, you know, mergers of black holes and things like that. We can use our models to get a new way to solve those kinds of equations. We can use our models to get a better way to optimize quantum computing circuits and things. Those are things which come out of our models as a formal matter. It's not a question of I'm going to build a device. It's a question of I'm going to use this as part of figuring out how to do other kinds of things, sort of almost as a better mathematics, so to speak, rather than a better technology. It's a better mathematical technology rather than a better physical technology, so to speak. And I think we're seeing the same kind of thing, particularly in distributed computing and probably distributed blockchain, of a physics-informed approach to those areas. The big thing is that in an area like distributed computing, it's part of what is the question. Like you say, you've got all these processors, they're all running separately. What do you want it to do? Well, the thing that happens is because of this interplay with physics, we can use this vast amount of knowledge that has been accumulated in physics to kind of inform our intuition about what it's possible to do with distributed computing. And that's, I think, a really fertile area, a place where we will see a bunch of applications in the very near term to our physics project, even though they're not directly sort of physical things. They're not like building a giant particle accelerator or doing something like that. I mean, there will be things that we might be able to see as pieces of experiments, of seeing things about the cosmic microwave background from the beginning of the universe, or seeing things about particular kinds of black holes and so on. But those are not technological applications anytime soon. I mean, I think there may come a moment at some point in the future of our civilization when black holes become a technological component. They're certainly not there yet. All right, I think we should wrap up here. Lots of interesting questions, a good place to start for next time. So thanks for joining me, and see you next time.